born with the vision of creating a united community of individuals that basically have similar aspirations for the space sector. We are working to make this vision a reality through our mission, that is to help develop the space ecosystem in Romania. And to do this, we have various activities ongoing, such as educational programs, hands-on technical projects, and community events. These are also the three pillars of ROSPIN, of our NGO. Now, ROSPIN Academy is our first, chronologically speaking at least, educational program, and it targets university students from Romania. The first edition took place a little over a year ago, and based on all the lessons learned and the experience we gathered from this pilot, we are now running this program with an annual recurrence, and it has 3 levels of increasing difficulty. So the first level of edition 2, it took place in October and November of last year, where we covered introductory topics about the spectre as a whole. So high level, we didn't get very technical then. We talked about the past, the present, the future of the sector, old space versus new space, space debris, sustainability, space law and policy, and so on. Now we are in level 2. Our participants now have the chance to learn about what happens in each phase of a typical space mission, all the way from feasibility studies, design, manufacture, assembly, integration and test, launch, and of course, operations. Also, you will notice we are speaking in English, although we are a Romanian initiative and it's a national effort. This is for several reasons. First of all, we think it's valuable for our participants to practice their English and to learn about these things directly in an international language that is basically essential if you want to join the sector. And it has also allowed us to have speakers, international speakers. We've had speakers from Poland, from Germany, from the UK, from the US as well, and so on, from Spain, and the list continues. So far, more than 400 people have been accepted as participants in this program across all of the editions and levels. So, going back to the present and to tonight, our participants will gain an introductory insight into the technology that is behind rockets and launchers. They will understand how complex spacecraft actually get into space. And yeah, because of the popularity of this topic and the invaluable presence of our keynote speaker, we have decided to organize this as a demo, where several external guests can join to get a bit of a sneak peek into what the Academy experience looks like. So we have about 45 minutes of presentation. Then we will continue with the Q&A, for which we also have about 45 minutes. We will first take questions from the official participants of ROSPIN Academy. And then, depending on the time that we still have available, we will open the floor to also our external guests. This is also the reason why we kindly asked our external guests to put the word guest in front of their name when joining WebEx, so we can easily distinguish who is who. So, after all of this, I hope I didn't talk for too long. I give the floor to our amazing speaker to take it away. Thank you so much for being here with us.
Good idea to unmute yourself. Thank you, Maria, for this introduction. And without further ado, let's go a little bit into the review of rocketry and launchers. I'm going to, well, first of all, I need to share my screen. Seconds. Okay. So we're going to talk rockets and launch in general, with a little bit of details into the workhorse engine that is currently used in the launching industry throughout the world. And then, of course, open for questions. The rockets, we're all seeing them on TV and study about them if you're in an aerospace program of some sort. The typical shape of the rockets of the collection you see here is basically the only proven technology that's being used for space. There are some newer ones that you might find as a, for now, maybe a curiosity. The newest one is the Slinger, this big wheel that slings small payload into space. I calculated that the G-forces experienced by that payload are on the hundreds and thousands. So only a very specialized type of payload can be launched into space with that type of technology. And there are some other ideas, but for now, we're using the proven rockets to put up in space various satellites. We're all using them right now when you pick up your phone, although you're picked up by a nearby tower with a signal. Now that we're discussing, or if you talk to a friend abroad, you're going through a satellite. As there are civilians, the military and government for observation, mixed. There are now very advanced services that sell crop information and weather information, of course, and so forth. Until about 10, 15 years ago, this was a industry based on governmental initiatives and money. No longer, as you're very much aware, there is a new wave, and it was the first wave of private launchers like SpaceX and Orbital Sciences, now Northrop Grumman. And it is a second wave coming. We'll talk a little bit about the many startups that are brewing right now. The launching industry is very dynamic. The number of satellites, I was lecturing about this topic until about 5 years ago, where the numbers were 1,500 satellites total launched until about 10 years ago, out of which, 5,000 total, out of which only 1,500 were active. The rest of them were just dead without batteries or extinguishing their fuel supply. But in the last 10 years, especially with the advent of this new idea of low Earth orbit constellation of large number of satellites that is being pushed by SpaceX, Starlink, the industry numbers are just exploding. So if currently the launching industry is overall the aerospace business, it's a 271 billion with about 5 to 6 billion in launch services only. Just the launch services will expand by about to about 30 billion by 2030. So lots of rockets coming in to provide all these services. Mind you that there was a false start in the mid 1990s where there was an early anticipation of such big constellations. Iridium is the best example of such a constellation which actually went bankrupt. Technology was not there. So this time, most of the specialists are agreeing that this wave is for real and that only environmental concerns or maybe geostrategic concerns may limit the amount of satellites that we're going to see on the skies. The industry is diversifying. While, as I mentioned, this was exclusively a government business until about 10, 15 years ago, SpaceX entered the market with the Malaysian paid payload of a Space Falcon 1 rocket. We're talking about the very first small rocket that SpaceX developed with only one engine. There were some other early developments that are listed here, but they never went commercial. SpaceX is the first one that got paid for a payload. And while all over the world, most of the countries listed there: China, Russia, European Union, Japan, India. They're all using government-paid and government-owned, in most cases, services. In the United States, it's been always the case that a government-sponsored private operator was doing all these launches. Even today, SpaceX, being a privately owned enterprise where most of the hardware has been developed on their own, there has been obvious and not that obvious significant government support. But the formula has changed from, say, 10, 20, 15, 20 years ago, where the government was heavily subsidizing the development of rockets, where now the new developers are looking for their own business models. For instance, SpaceX wants to launch the Starlink network, where they anticipate a large amount of revenue, and only a fraction of their business is government. There are new venues, of course. You've heard about the space tourism, like Blue Origin and Virgin Orbit, launching people in suborbital altitudes. There are extremely new many startups that are developing newer launch systems. I'm quoting here Relativity Space, ABL, or Rocket Lab. Rocket Lab, which until now has been using a rocket with electric motors running the turbopumps. We'll learn in a couple of minutes about turbopumps. They quickly reached the upper limit of their weight. They get put into space with electric motors, and now they're also lining up in developing the good old and proven liquid propellant rocket engine, of which we're going to learn today. The solid fuel rockets are used, but in a limited way. We're going to talk in a couple of minutes about Omega A and NASA RS-1, but most of the solid rocket boosters are used either as auxiliary rockets. When you're looking at a launch, you'll see this little side boosters that are being attached to the main rocket, and they are increasing the capability of that rocket to lift a payload into low Earth orbit. And very few uses, if any, were meant to be as a main rocket. And I'm going to show you in the next chart the story of RS-1, which was meant back in 2005, 2010 or so, as a man-crewed rocket to space within the program known as the Constellation. What you can see here is the very first concept. It was using the SRB, the solid rocket booster that was used for the space shuttle. If you're looking at pictures of the space shuttle, you see that in the two sides of the big hydrogen tank, there were two of these boosters, and together they achieved the necessary thrust to launch the shuttle into space. There was an idea during the Constellation program, which was meant to take the Americans back to the moon after the Apollo missions, 50 years after that, to use this entirely solid rocket boosters power rockets. This idea was not favored by everybody at NASA. I mentioned that in my previous presentations, and you could see the number of ideas and developments that were proposed. In essence, they quickly realized that the solid rocket booster does not provide enough of a length of burning, not the thrust itself. They wanted to have it operating more to bring the upper stage, which was powered by a J2X engine, into low Earth orbit and beyond. So for that, they said, well, we will add another segment. The original boosters had 4 segments, and they added another 5th segment of the solid rocket to enhance and extend the burning time, which then brought a lot of complications. These boosters remained towards the end of the burn. The burn occurs from the center towards the outer wall, and at the end, this tube is almost empty, and with the extension, it there was an anticipated increase in vibration, like a organ tube, if you want, and so forth. All these complications in the persistence of this idea led, among other things, to the cancellation of the program. However, while this was left at the drawing board, later Northrop Grumman, which inherited the chain of consolidations of the corporations. Originally, this was Thiokol, then ATK, then Orbital ATK. Then Orbital ATK was purchased by Northrop Grumman, and during a contest in the 2012-2013 timeframe, if I remember right, where the United States government asked for bids for 3 rocket systems to be proposed as the baseline for the future American launches, where only 2 of them would have been selected in the end. Northrop Grumman participated with this Omega rocket, which you can see it's a clear inheritor of the Ares-1 technology. Fortunately, they lost and they canceled the program. The selection was awarded to SpaceX and United Launch Alliance, a corporation formed by Lockheed Martin and Boeing Company. On various rockets, historically and present, of course, the tendency is to increase the payload capacity. For satellites and commercial satellites, from 10 to 25 tons to low Earth orbit, which is a metric to compare, is enough. But when it comes to man-crewed missions, say to the moon or beyond Mars, you need more capacity, because not only you have to lift the crew in space, but you have to lift the upper stages that are then burning one after another in order to penetrate the deep space with a flight. So the reference remains the 140 tons that was achieved in 1960s by the Saturn V rockets, powered by 5 F1 engines, each of them with about 1.5 million pounds of thrust. I'll list in a minute the thrust in newtons and SI units. But you can see here that 140 tons, it's hard to match today. Even the Space Launch System, which will soon launch in May, it's only at 95 tons at this Block 1 configuration, anticipated to increase to about 130 tons in a Block 2 cargo. And these plans are changing as we speak, because various developments are being considered by NASA. The Starship, which will soon hopefully fly from the SpaceX, it's now going beyond that number with a projected 150 tons when this rocket reaches maturity. And as I was discussing with the ROSPIN organizers earlier on, I'm not following in very detail all these developments, of being preoccupied with my own fraction of work in the industry. And I recommend, for those of you passionate and want it to be up to date, a website being maintained by Claudiu Tănăsălia, a very expert and specialized parser of news and classifications of various vehicles. Parsec.ro is a website to follow. So let's talk now about rocket propulsion, where the workhorse is the chemical liquid propellant rocket engine. We'll talk about the principles of these rockets and some of the details as to where their cycle is, and or cycles are, because there are several, and some of the inner workings. And you will learn in the end of this lecture to browse the internet and follow a diagram and the operation of these engines as they come. Needless to say, this technology is old, and as old as World War II. In fact, earlier than that, Professor Goddard here in the States was tinkering with these rockets. The principles of rockets and penetrating space are even older, from the Russian scientist Tsiolkovsky, and then technology followed. During the war, of course, the Germans developed the V2 rocket. Herbert Wilhelm von Braun and Werner von Braun and our co-national Hermann Oberth among the principal people. While the technology and the principle is old, the technology evolves, especially via the progress in materials, special alloys, and of course analysis. We have many very advanced tools of analysis, so we can craft these engines in a better structural way to achieve higher pressures and temperatures. And what we're talking about of power or energy density of turbomachinery, there is turbines and pumps that vehiculate fluids at such a high energy that is one order of magnitude above the jet engines that we see every day in airplanes or helicopters. Not less important is the ability to control these engines via microchips and computers manufactured in a way to resist vibrations and various other adverse elements. And also what the Russians, for instance, didn't have for the Rocket N1, which had, I believe, 50 engines or so, attempting to use multiple engines in a way to generate enough thrust to go to the moon with all these upper stages. The controls available at that era generated instabilities in the operation of so many engines that this very expensive Russian or Soviet rocket was launched twice, and twice it failed in an exceptional way with spectacular explosions. Besides this liquid propellant rocket engine, the chemical one, there are other principles which were developed and proven, among which is the nuclear thermal. We'll talk about temperatures developed here at the core, which in the chemical engines is obtained by combustion. For the nuclear thermal, the fluid is just flown through core of nuclear fission reactor, so to speak, where the source of the heat is just the radiation itself. Was demonstrated. It's even more performant, the chemical rocket, but there is the perceived public risk of flying nuclear material in space, and for that reason is not yet employed. It's in the planning, however. And of course, there is the electric propulsion, small thrusters that have a very low thrust but extremely efficient operation, which are used for satellite navigation, station keeping, or even achieving deep space flight. That is, probes that go to Mars, Jupiter, and so forth. So the principle of rocket propulsion is simple. Some of you may study it in school, and for some of you it's new, so I will just assume that for everyone is a good intro is welcome. It's the principle is the Newton's third law. Action provokes reaction. We have a recipient of high pressure gas and temperature that we engineered in a way that it expels a mass flow of hot propellant towards my right. And of course, that continuous mass flow of fluid generates reaction of the entire recipient and its extended nozzle towards the left, and we obtain thrust. There are, of course, various details here. When we look at the thrust equation, we see that the major term here is the product between the amount of mass flow of propellant that we're expelling and the velocity of that propellant. So that's a major component of the thrust. And then there is a play of pressure here at the exit of the rocket nozzle, where depending on which is the gas pressure, PE, versus the atmospheric pressure or ambient, PA, can generate a plus of thrust or a minus of thrust. So the game that's being played here, it's different for boosters that start on the ground and for upper stages that operate only in space. This typical shape of rocket engine, which is called the de Laval nozzle, is engineered in a way where the narrowest part, which is called the throat, achieves the fluid velocity here that's exactly the same velocity as the speed of sound at the same location. So we call this a sonic regime, that is Mach is exactly equal to 1. And then it's expanding after the sonic regime, the flow expands. And as the law of gas dynamics show, when you have an expanding area, the flow expands to velocity that are larger than sonic, which we call them supersonic. The only problem here is that as you expand to supersonic velocities, your pressure of the fluid, local pressure, is diminishing gradually, more and more and more, until you get to a certain pressure at the exit, PE. So here is the game we're playing. We would like to expand this as much as possible, drop the pressure, but obtain as large a velocity as possible, because this VE velocity is proportional to the ratio of this area, A star to AE. But if we expand too much and the pressure is much lower than the ambient, then we are then obtaining a negative term on the thrust. And not only that, but we experience shocks here in the throat, which are meant to re-equalize the pressures. So for booster engines, the engines that start at the low level, sea level or low altitude, we see this expansion relatively limited. In space, where actually that PA is 0 in vacuum, then we use these expanded nozzles as large as technologically possible to manufacture, or structurally possible to withstand the pressures that are being expanded without collapsing. Well, while the principle is simple, the idea is that, well, we can start with a nice chamber with enough pressure and temperature in it, but as soon as we expel the gas, this empties, and we're left with no thrust. So for that reason, for practical purposes, we need to have two tanks, one of fuel, one of oxidizer, and through a mixer and injector, feed them continuously into the rocket engine to maintain this operation and thrust, typically for 150 to 200 seconds during the booster part of the launch, and the upper stages longer thrust to maybe 300 to 400 seconds. So obviously we put these two propellants into tanks attached to the rocket, and then continuously feed them into the rocket engine. Then more interesting problems appear from the engineering point of view. We want this chamber pressurized as high as possible. The higher the pressure, the more expansion we can get towards the ambient and get more thrust. The first idea is to put these two propellants into tanks that are pressurized really high, and then just feed them through some regulation valves into the rocket and maintain thrust. The problem with this idea is that in order to pressurize these tanks at such a high pressure that we need for the rocket, we need to build really strong walls for these tanks, and obviously then you end up with a very heavy rocket. So Professor Goddard, all the way down back in the 1930s, realized that a better idea is to build thin-walled tanks, pressurized at maybe 3 to 4 atmospheres, and then feed the propellants, fuel and oxidizer, into the engine via what we call turbo pumps. That is, pumps that suck the propellant from the tank pressurize it to these ducts and feed the engine. And then the next problem came as to, okay, where do we get the power to power these pumps? The amount of fuel, to go back to this thickness of the tanks, this is a study also during the Constellation program. I borrowed this chart to show you that while the engines are this small compared to the structure of the rocket, most of the rocket is just tanks. These tanks of oxidizer and fuel, this is for the lower first stage, this is for the second stage, are the most part of the body of the rocket. So if you make them thick, then you end up with a very heavy rocket. You need these turbopumps to feed the rocket engine. So you'll see that the powering of these turbopumps is done by turbines. Many times I get the question as, why do you need turbines for rockets? We need those turbines in order to power these pumps that feed the rocket engine. And the very first turbopumps, there is a turbine on one end and the pump on the other end that are being installed into the rocket engines. They were developed first in the USA and in Russia, in Soviet Russia at the time, in 1930s. Here in the States was Robert Goddard, and I'll show you some pictures. The very first flight, in fact, was in Germany. I don't know if you know, but the Germans, while the U.S. Army was not that interested in Robert Goddard's ideas, Germany was at the opposite end. They had representatives here in the States that would go daily to the patent office in Washington, D.C., and search to the patents that may have been filed by Goddard and immediately send them by courier to Germany. So Germany recognized the power of this rocket technology, and the very first turbopump-powered rocket was, in fact, flown in Germany in 1939. You can see here some of the details. I want to go back to something that I didn't emphasize. One measure of the efficiency of the rocket engine is what is called the ISP, the specific impulse. This is measured as follows. Take the thrust that you obtain from the engine and integrate it over time. And basically you add all the amount of time that the engine operated with thrust and divide this by the entire mass of propellant that's been stored in the rocket. And then the result would be a number that's expressed in seconds. And for a chemical rocket engine of very good performance, this ISP has a number of about 400 to 420. Then that's for hydrogen and LOX propellants. For LOX and RP, this ISP is in the mid to low 300s, and for other combinations is lower. So would they specify that this very first engine had a very low ISP for the time. It's a very first turbopump powered rocket, 145 and 150 seconds ISP with this propellant. It was the Messerschmitt 163 engine, then followed, I'm going to show in a picture in a second. Then the V2 engines developed by von Braun, then developed the pace of the turbopump in the modern engines that we're seeing today. This is Robert Goddard, one of his early rockets, somewhere in hidden in a small turbopump. Interesting, here is the Messerschmitt 163 engine. It was powering this very small aircraft. Germans were desperate in 1945 and 46 to have an airplane that would take off extremely fast and meet the incoming bombers from England and United States coming to massively bomb Germany. And this was the technology response that Germany did. It was powered by a rocket engine that you see here. somewhere here is the turbopump assembly, a very long extension in the rocket engine. You could see very little expansion. These were not very performant engines. Here is the V2 rocket, where the turbopump that I mentioned, the two big tanks, and in fact, the warhead that was making so much destruction in London and Amsterdam, it's only this small part of the rocket. Goddard decided to try put turbines in the extremities, in the fringes, in the lateral sides of the jet. Bad idea, because the rocket jet is extremely hot, on the order of 6,000 Fahrenheit, 4,000 degrees Celsius. These turbines will melt in a very quick period of times. The other lesson that we're learned is that when you suck the propellant from the tanks at relatively low pressure, the pump experiences cavitation. That is, the fluid develops vapor, and when the vapor collapses in the metal of the blades, it generates destruction, which in a minute or two can destroy your entire engine. And they developed this technology called the inducer, this screw type of part of the pump that sucks the low pressure fuel, increases its pressure a little bit, and that routes it to the main part of the pump. So, as I mentioned to you, the placement of these turbines and how you organize the cycle of the rocket engine is basically determine the nature of the rocket engine. What Werner von Braun did is to realize that you can't put the turbines here in the nozzle. It's too hot. So then we would organize a small combustion chamber where we would mix propellants in a different mixture ratio. That is, we'll make the gas relatively colder compared to the rocket. We will put this gas through the turbine. That turbine then will power the two pumps. In this particular case, they are on the same shaft. One turbine powers both pumps, but this then, whatever fluid we're using for the turbine will be then thrown away. While this is a good idea, this fluid is colder, the turbine operates properly. This mass of fluid that we're throwing away then does not participate in the turbine, in the rocket thrust equation, so we're losing it. This cycle is called the GG cycle, from the gas generator cycle. It's one of the first one, and you could see here the V2 turbopump, where the turbine is here in the middle. This is the inlet, and somewhere in the back is the discharge, and this is the fuel pump, and then this is the oxidizer pump that are being powered together. This is the V2 rocket. Immediately after the war, of course, the winning powers, both Russians and Anglo-Americans, borrowed not only the technology, but the scientists themselves. Werner von Braun and about 100 people in the States, many other in Russia. And you could see that the immediate technologies developed after the war in both Russia, USSR, and in the United States under the name of Redstone are essentially replicas of the original V2 engines. And I had the opportunity to take a look at the Redstone turbopumps right in the backyard of Rocketdyne, where I worked in the late 90s and early 2000s. So the original cycle that was employed by von Braun and later on even by the F1 engine that powered the Apollo booster had then various other developments. One of them is, for instance, the GG cycle, where the fluid obtained in the gas generator is split into two, and you have two turbines, each of them powering the attached pump. Why would that be? Well, here we're having a cycle that is using kerosene and liquid oxygen. These two fluids have very similar densities. the pumps are centrifugal pumps that operate by swirling the flow of this particular density centrifugally and obtaining that large pressure that you need for the rocket combustion chamber. When we're moving then into a cycle where we have on one end hydrogen and on the end oxidizer, such as LOX, the density of the hydrogen is about 15 to 16 times lower than that of the oxidizer. So in order to obtain similar pressures, the hydrogen pump has to rotate much faster. So you cannot have the same turbine powering the same shaft because the fuel pump wants to spin faster. So you absolutely have to split the configuration of the engine in two turbo pumps to operate them separately at the necessary speeds. You could do this in parallel, like here. This is a very example is the RS-68 engine of the Delta IV rockets. Or you could organize them into a series where you generate the gas, you power first the fuel turbo pump, much faster speed. Whatever energy is left of the fluid after that turbo turbine, the fuel turbine, you power, route it into the oxidizer turbine that needs lower speed, so relatively lower power, and then you dump it overboard. Okay. In all these cycles, the common element is that whatever you're using in the GG, you're dumping it overboard, and you're losing some of the mass flow that you need for the rocket thrust. Here's an example of the image of the F1 engine. This is the Apollo era Saturn V engine. Excuse me. Hello? Yes, sir. Yes, I'm sorry. I'm in a presentation here. We have to talk later. Thank you. Such as, sorry. We're talking about Saturn. This turbo pump is the largest built. Not even the RD-180 has such a large pump. We don't know much details about the engines of the Long March 9 that is being developed now in China. But this is a pump that weighs 1.1 tons. And it's the typical example of a single shaft. You could see it, the turbine at one end. And here is the oxidizer, the fuel pump here and the oxidizer pump on the opposite shaft. A more detailed example of the J2 engine with the two turbines in series. This is the gas generator. This is how you read this. Turbines. There is a gas generator here fed by both propellants. The small amount of flow that's being generated is being fed first into the fuel turbine and then into the LOX turbine, and then whatever is left out of both turbines, it's then, instead of being fed or thrown overboard, in this particular case, it's being dumped through a heat exchanger that picks up the remaining heat of the fluid to warm up oxidizer for tank pressurization. And then what's left of this fluid is being injected through this little ring into the extension of the nozzle. J2X is an upper stage nozzle that has a very large extension cone, and it's very hard to cool that cone. So one of these technologies is to take the fluid of the turbines and inject it along the walls. It's a hot fluid, but not as hot as the main fluid of the rocket engine, and you're cooling this rest of the nozzles. The typical cross sections of turbo pumps are shown here for J2X and the oxidizer. This is the oxidizer as being flown during the Apollo times. a very hot two-stage turbine and a very cold liquid oxygen pump. And you can imagine the type of engineering you have to employ to hold this together at minus 100 degrees Celsius to plus 1,000 degrees Celsius on the other end. This is the old version, and this is a heavily censored for publications. The cross section was used for the J2X during the Constellation program. The same here for the fuel pump. The original fuel pump, mind you, developed by the Germans that were still working for NASA at the time, had an axial pump. This inducer that I mentioned to you, plus something that looks like a compressor today, whereas for the latest development, the Rocketdyne engineers have used a centrifugal pump, where the inducer would be coupled with a centrifugal pump and another two-stage turbine. The late 70s, also having von Braun still working at NASA, has brought another more advanced cycle, which was called the stage combustion cycle. The Germans and the NASA scientists were unhappy with the fact that some part of the amount of fuel had to be dumped overboard via the GG cycle and not used in the production of the rocket thrust. So from this point of view, they've introduced the stage combustion cycle, where they would take the fuel fluid from the pump, route it through cooling the entire engine, and then go and split it into two GG types. We call them pre-burners, where a little bit of oxygen would be introduced, such that they would produce gas with a certain pressure and temperature, but not too hot. And then the resulting fluid would be routed through two turbines, again, fuel, hydrogen, and oxygen, liquid oxygen. And then the remaining, whatever hot gas remains from the turbine, would be just injected into the main rocket and expanded. Here is what we call the power head. The two pre-burners, one here and one here, that dumps the fluid into the two turbines, then it's being routed through these collectors into the main engine. And each of these turbines is powering the very high pressure pumps. These are more details of these turbo pumps. This new cycle, besides having the advantage of generating much larger pressures for the rocket engine, and therefore a much more performant engine, also had the full utilization of the fluids, so no mass flow was being dumped overboard. The unfortunate part here, the compromise, was the fact that the engineers did not want to flow through these turbines anything other than hydrogen and steam. When you combust in the pre-burner hydrogen and a little bit of oxygen, you get hot steam combined with rich hydrogen. For that reason, these turbines are relatively small and have more than two stages, and they are operating relatively hot in order to get the necessary power to rotate these massive pumps. The same here for oxidizer turbo pump. You need 3 stages of fluid, 3 stages of turbines to route to flow that relatively small amount of fluid and power this massive oxidizer pump. The Russians, in parallel to this development, had developed another critical technologies. They developed materials that were compatible with high pressure oxygen. In the rocket, you have more mass flow of oxygen than mass flow of fuel, be it hydrogen or kerosene. So if you are able to develop a large turbine that can flow high pressure and high temperature oxygen without exploding, in high pressure, high temperature oxygen, if you're rubbing metal against metal or you have other incident like that, like a part breaking a little bit from somewhere in the engine, that happens sometimes, and impacting on the blades, uh, surrounded by high pressure, high temp oxygen, this entire thing goes kaboom. The Russians have developed this set of alloys, and that they've developed the oxygen-rich turbo pumps. That is, in the preburner, instead of having a majority hydrogen plus a little oxygen, they would fly the entire mass of oxygen with a little bit of hydrogen, so producing a high pressure, high temperature gaseous oxygen with a little bit of steam into it and pushing it through the turbine. And of course, kerosene and oxygen have very similar densities, and they would do this through a single turbo shaft. Here you go. This is a cross section of RD-180 or RD-170 family of engines. These are extremely performant engines. While they produce about half of the thrust of an F1 engine, they have a better ISP of 311 seconds compared to the 265 of the F1 engine. Naturally, the fact that that material that was initially developed by the Russians existed has generated finally the most advanced and currently used engine, which is called the full flow engine. Instead of having all hydrogen split into or all oxygen going for the full turbine, this engine takes the fuel, let's say hydrogen, under high pressure. Then first it's cooling off the skirt and the combustion chamber of the main rocket engine, and then goes to a preburner or a GG, which is then fed with a little bit of oxygen. So it produces a flow of majority hydrogen plus a little bit of steam through a single stage turbine. The oxidizer, the LOX, it goes through a pump, high pressure, goes to another preburner, which is fed with just a little bit of hydrogen, and it produces a mixture of high pressure, high temperature oxygen with a little bit of steam, pass through another single stage turbine and powers the oxidizer pump. This way, you have relatively cold flows with a large mass that powers two turbines, and then everything this gets collected into the rocket engine and produces thrust. This is the more elaborate version of the RD-180 engine. And I'm going to point here to another development that has been achieved, in the sense that if you remember the cavitation that destroys your pump, instead of feeding your main turbo pump with low pressure fuel or LOX from the tanks, not the Russians, but the United States has used as well the technology of the boost pumps. There is some small pumps that will initially boost up the pressure of the tanks to a level that will avoid cavitation in the main turbo pump. So this is the fuel tank going through a boost pump, then going to the main pump, and then distributed here in the RD-180. It's more to explain than we have time here. Russians do not manage well the combustion instability, so that's why they use the large turbo pump then feeding two small rocket engines with combustion chambers small enough that they are able to control the instabilities. So fuel goes into the main turbo pump, then is being split to feed the two engines. Then LOX gets into the pump, then most of the LOX is getting fed into this preburner through the turbine, and the gas from the two turbines is being fed to the two engines, mixed, and gets into the rocket engines. And this is helped by these two boost turbo pumps, which essentially consist of a large inducer and the small tip turbine that is just powering that turbo pump. Other than that, we have upper stages. I'm showing here the installation of the RD of the RL10 into the Centaur upper stage or the J2X in the Saturn upper stages. These are the same type of rockets, chemical rockets, with adapted though for operation in vacuum. You can see here the same turbopump based engine for the RL10 schematic. Where the solution of spinning the two pumps with different speeds was done in a different way. We have only one turbine that rotates very fast and operates the hydrogen pump very fast, as I said, but then the speed is reduced via a satellite type of gears into the oxidizer pump, then feeds the main combustion chamber. This is also another type of cycle where there is no combustion for the turbo pump especially. Instead, the liquid hydrogen that is being discharged from the pumps is being routed as usual to cool the skirt and the main chamber. And then warm as it is not hot, but warm, it has enough energy to go through the turbine and being then rerouted into the main turbopump, so into the main chamber of the rocket. So therefore, the energy used for the turbine is essentially the heat that's being picked up by cooling the engine. These are called expanding cycles. So we're getting closer now to a summary. In the future, the way I see it, the stage combustion cycle, this particular one, it's probably the future. Everybody's developing this. These are the SpaceX Raptors. It was demonstrated by Aerojet Rocketdyne in 2005, and there are other companies that are using them. The new smaller startups like ABL or Relativity Space, even the Rocket Lab, they are going back to GG cycles because they are the cheaper, the most proven, and these companies are targeting a relatively small, narrow niche of 500 to 1,000 kilograms of satellites launches, not big ones. And then we will see how the market will select through all these companies. It is clear to me that the financial market of launch industry cannot sustain everybody that's trying now to develop rocket engines. We will see how this will pan out. Technology-wise, NASA is not experiencing with new cycles, but new form of fabrication. And I'm showing here some examples. NASA has generated a full engine printed, 3D geometry printed. They do that by trial and error, where you're working with very many suppliers that print for them. They're not just printing them themselves. And there are a lot of feedbacks and shortcomings to these technologies, but they managed to test 2 turbopumps and 1 engine. And you see here examples of parts being 3D printed and then a surface finished by one technology or another. This is very important because those of you who may have been involved in 3D printing saw that the surfaces obtained are very rough and they are not really good for fluid flow. Of course, you have housings. So 3D printing is extremely good for housings because otherwise you have to cast them, and casting of complicated housing takes months and months to develop. So in the future, the liquid propellant chemical rocket will still be the workhorse. All these new companies are developing one version or another of liquid propulsion. There are no new conceptual cycles except fabrication. And depending on what the business models will prove to be efficient in the future, either big geostationary satellites or many LEO satellites that are of the type of Starlink or Kuiper from Blue Origin. We'll have to see, and they will decide which of these new companies will stay in business or will have to close. Last but not least, I encourage you to examine a book. I happen to be able to write a thriller, which I wanted to write especially to get the reader a feel of the inner workings of the aerospace industry and the necessary parts that is personal parts that are involved in such a life. And also the fact that, as I mentioned to you, if by any chance someone will have a new principle of a new rocket engines to push that 140 tons limit into, say, 500 tons, that will be a disrupting financial market in the rocket business, as well as geopolitical power. So with this, I conclude my presentation, and I'm looking forward to receive your questions. Thank you.
Wow, that was an amazing presentation. For me personally, it kind of took me back to second year propulsion. Like everything in there was very interesting. And now we don't have a lot of time for Q&A, so I hope people get going with questions. We first want to take questions from ROSPIN Academy participants. So please go ahead. And either way, anybody can start writing questions in the chat, or you can unmute yourself.
I hope I can answer all these questions. Yeah.
If people don't get going, I definitely have some. So
while people are thinking about their questions, writing them, or I don't know, making the courage to unmute themselves and ask them directly, I would like, as usual, to ask everyone to turn on their cameras. We can take a few virtual group pictures and so on. And okay, we got the first question in the meantime.
I'm not sure if let me see if I could look at the chat. I think there.
So we have a first question, which is about the spin launch test. So what are your views on the recent spin launch test? You mentioned them at the beginning of your presentation.
I mentioned that my view on the spin launch is that if successful, we'll have a narrow use. I explained that the rotation of that big wheel of 12 or 15 or 16 meters is subjecting that payload to G forces, to acceleration forces, like you experience when you turn very tightly with a vehicle, but on the order of 1,000 Gs. This is something that would crush most of the structures of a typical satellite, like a communication satellite. So the types of payloads that the spin launch will be able to launch are something like solid state CubeSats, something that would have an extremely strong structure and would be very specialized. We'll have to see what those are, but that's the major limitation of that technology, the strong G-forces that are experienced by the payload.
I would have like a follow-up question. Do you have any idea about the time frame that the load is applied? Is it closer to a shock load, or is it like a steady state 1,000 G load?
It's well, the way this works, my understanding is that this big wheel is accelerating in a limited amount of time from zero rotation to whatever RPM it needs to launch the payload. So it's not a sudden rotation. It's not like you're rotating within 2 seconds, you get to that. So it's building in time. So obviously the payload will sustain that G for at least 2, 3, 4 seconds or more until it's being released. So it's an extended time. I would say tens of seconds of exposure to high Gs.
Okay, that's quite significant. We have a couple more questions now from the audience. So Vlad is asking if you have any thoughts on expander or bleed/open expander cycle engines. He knows that Japanese designs use that cycle to overcome the thrust limit of the traditional closed expander cycle.
I'm not sure if they overcome the limit. They are using their fond of the closed expander cycles. The open expander cycle has the same disadvantage of the GG cycle. That is, whatever fluid you're using for the turbines, you're throwing it away, or if it's an upper stage, you're just using it to cool the nozzle. The closed expander are pretty much similar to the RL10. And what you could do is optimize it through a distribution of pressures and temperatures and turbopump rotations. But these cycles are pretty much similar to the, say, full flow cycles in terms of performance. The Japanese also prefer LOX hydrogen. Back at the Rocketdyne time, we had a project with Mitsubishi Heavy Industries called MB60, so Mitsubishi Boeing. Rocketdyne was part of Boeing at the time. It was called MB60 because we were targeting a 60,000 pounds of thrust divided by about 2 to get kilogram force. And it was meant to replace the RL10 for the Delta rockets at the time. This was part of the first wave that I mentioned, where everybody believed it's going to be a bonanza of launching in space, which was then stopped by the Iridium bankruptcy. So back to Vlad's question, they are improving these engines and maybe add 1 or 2 seconds of ISP, but not much more, in my opinion.
Oh, thank you very much. We have another question from Alexandru. He wanted to ask you how close we are to reliable commercial suborbital flights at the moment.
No, I have to explain that, or maybe Alex knows that suborbital means you're not on orbit. So you go up and then come down where you have reached you beyond the von Karman limit of about 100 kilometers or so. There is less commercial use for the suborbital flight other than tourism, from where I see it, because from the suborbital flight is a relatively short flight, not a long presence in space, and you cannot use, say, this for communication. So suborbital flights at this time are now being used by Blue Origin almost routinely with the New Shepard for essentially, it's a very expensive Disneyland, if you want. You go in space and experience a couple of minutes. On the order of 15 minutes of no gravity. You see, obviously, the space and the lights and so forth. Everybody's getting excited, but that's pretty much the entire use of it. And the same with Virgin Orbit, where you launch on this rocket carried by the carrier airplane up to 40,000 feet or so. Then you take off into another type of suborbital flight.
Okay. Until I think Albert is writing the question at the moment, until he puts that in the chat, I wanted to go back a little bit actually towards the end of your presentation where you mentioned 3D printing. I wanted to ask you, how is the advancement in additive manufacturing in general changing the design philosophy for rocket engines and maybe the assembly of rocket engines?
There are many ideas being promoted. In essence, the 3D printing has allowed rapid prototyping and continues to allow it. No matter if you choose 3D printing for your final product or not, then to get one of these complicated housings, not just for the turbo pumps, but for the engine themselves, it's a great advantage. So the rapid prototyping is one thing. The other advantage is that you diminish the amount of parts that you're having. For instance, the main chamber injectors have a lot of small channels and convoluted fluid trajectories in order to optimize that mixing. To do that in the old type of technology with lots of tubes and brazing them, basically welding them in a specific way, takes a huge amount of time. So 3D printing is improving all that. In my opinion, 3D printing will never be a reliable technology for rotating parts because the extreme centrifugal and other type of structural solicitations of these parts and the type of voids that sometimes you get into the 3D printing may have shortcomings. As I showed there, it's important to have proper technologies to obtain a desired surface finish after you finish 3D printing. And then moving away from parts of rockets, one of the ideas that's being promoted by relativity space is that they want to print the entire rocket. And if you're looking at their webpage, it's essentially rockets. If you're looking at them, they appear complicated, but it's just lots of sheet metal rounded and welded, where you have basically you fill them up with propellant, and they are calculated in a way that, for instance, if you have a rocket prior to launch and you hit them with something heavy, it will quickly deform. These are very thin structures. But rolling all that sheet metal and putting it together is a lot of labor and time. So relativity thought, well, what if we just spin print them? And I know they've been searching for their technology for quite some time. And apparently they are reaching a maturity. Early on, I visited them. Incidentally, the founders, both founders of Relativity were my students back in the day at USC, so I know very well both of them. And their original printing was resulting in too heavy of a structure. And they were trying to improve that and obtain the proper ones, and apparently they are doing it.
Yeah, okay. Thank you very much.
Yeah.
Vlad has another question. He's asking whether you think we might see American domestic kerosene staged combustion designs now that the Russians' designs like the RD-180 are will no longer be available.
Yeah, it's a big priority, and yes, you will see them. Blue Origin will come up with their B4 engines. It's closer to maturity. Obviously, the Raptor engines, they are not RD-180 cycle, which uses a single turbine for both pumps, and because these new engines will not use kerosene. Kerosene has about 2/3 of the density of liquid oxygen, but the new fuel is methane or even LNG, liquefied natural gas, which is about 90-something% methane. That density is about 1/3 roughly of the liquid oxygen, so you are forced to use separate pumps. And for that reason, it will be the full flow cycle that's being promoted, both on Raptor engines and future other engines. B4 engine, as presented, it's more like the RD-180, where a single turbine is being used, in spite of having methane as the combustion, but as the fuel. But there are some specific engineering solutions to that.
Okay, thank you. I had another question. This one is related to rotation detonation engines.
I'm reading them, Adrian. I opened my chat. So frankly, I don't know anything about Kerbal Space Program 2. Sorry to Mr. Bogdan.
Oh, I missed that question. Yeah, maybe he was thinking about it as a teaching tool.
Yeah, I don't know anything about that. So it's like I said, maybe Parsec would definitely know something. Yeah.
Well, in any case, before we move to questions from the guests, if there are no more from the participants, I also remember in a previous lesson that we had, but that one was more focused on onboard propulsion, there was a question. If I remember correctly, it was about how is the reaction force handled on the launch pad or something along these lines. I believe the participant who asked that question is here with us today. So if he wants to clarify what was the question exactly, but maybe we can address that one.
You mean like how is the launch pad built so that the two reaction would not destroy the structure? Is that because I believe that's probably the question. In essence, the launch pad is not like a flat surface on which the rocket stands. The rocket is being supported laterally, and the jets are being flown backwards and then deflected by specific concrete surfaces. That's why when you see filmed, you see look at every YouTube video of a launch, you see very strong plumes going laterally. That's because the jet goes downwards and being deflected by a 45-degree angle. For here, I have a nice anecdote to speak. In the rocket terminology, the way the launches are going is that this rocket it's being kept on the side with some very strong support. And then you start these engines, usually they start within 2, 3, or 4 seconds. They stabilize and they reach maximum thrust. All the while, these claws of steel are holding the rocket there. They don't let it go. And when the maximum thrust, the takeoff thrust is achieved, then these claws are being released, and then the rocket takes off. That thrust that is achieved just a fraction of the second before the release, it's called in rocket terminology hard thrust. So when I published the book that I mentioned to you at the end, my very first title was Hard Thrust, which I thought, okay, it's a nice title. It's a nice little red herring because people will think, oh, maybe it's a pornographic something. Let's check it out. And then a friend of mine told me, a female friend of mine said, Bogdan, I love your book, but I just cannot read it in the airplane. Because if you open a book that says hard thrust and you're a lady and you're sitting in an airplane, people are looking really weird at you. So at various advice, I changed the title and re-edited the book. But during my time at SpaceX, it was still available as hard thrust on Amazon. It was a little cult book within the SpaceX people. And then Elon Musk was upgrading the Merlin engines, and he kept pushing the Falcon 9 rocket to new and new thrusts. And he was running out of titles. We was calling them super thrust and increased thrust and so forth. So during one period of time, we convinced them to call the new regime of the Merlin 1 engines hard thrust, which was official for only about 2 months, but we had a big kick out of that. So long answer to a short question. Yeah.
That's amazing. Going forward, Laurencio has a question about, well, let's say references and bibliography for engineers that start to shift their focus on the space sector. What books do you advise to study in the area of rocket design and simulation?
Let me find. There is a book edited by two Rocketdyne people that it was to many people amazement they were able to publish this book, but it has essentially the all elements of liquid rocket engines. So I'm going to put this link here for everyone to read. This is a beside. There are many others. There are Sutton, George Sutton's book, but this is a book edited by these two Husel and Huang authors that were working at Rocketdyne in the old times, and gives you the detailed calculations of the various elements of the rocket engine, starting from the main chamber through turbopumps, valves, and various other details.
Okay. Yeah, maybe it would be useful for the ROSPIN Academy students if you just send us a few references that we could pass on, so they could have a look at several of these books if they're passionate about propulsion. Until we get more questions, I wanted to ask you a little bit about rotation detonation engines, because there's especially recently there's been quite a bit of research in the area of RDEs, and I wanted your opinion on their feasibility and their stability issues.
Well, the progress has been tremendous. I recall, I mean, Rocketdyne was involved in that as well, together with Purdue University. So for those of you that might not be familiar, there is a way to introduce these two propellants into a main combustion chamber, and in the form of an annulus, where the mixture again is being lit, and it would burn in a detonating way. That is almost like a localized explosion. But that explosion is in the form of a sheet, so very thin front of flame, usually diagonal with respect to this annulus, which and could be one or two of them, and they will rotate very fast. So this is called rotating detonation. The advantage of this type of detonation is that you inject relatively low pressure combustion propellants, oxidizer and fuel, and then the end of the combustion produces a very high pressure and temperature. So in essence, once this is done in a very stable and controllable manner, you don't need turbopumps anymore. If you feed this rotating detonation wave chamber into, say, a rocket engine, then you are able to obtain rocket thrust without the neither thick tanks nor to the complication of turbopumps. In my opinion, watching this now and then, not being deeply involved in this kind of research, the stability of this phenomenon has been improving quite a bit, but it's not that they're yet to employ commercially or operationally. This can be done also for regular jet engines, where you would replace in part the compressor to obtain high pressures for the thrust of the jet engine with this rotating detonation. Many times I fly over the Atlantic back home, or coming back from Romania back to the States, and I'm thinking that just a couple of tens of meters from me, there are these hot turbine where everything is carefully cooled. If the channels through the nozzles of the high pressure turbine would not be operating properly, that blade, that vane would melt in a question of minutes, and it's not a good and pleasant thought to think of this while you're over the Atlantic. Now, if you're thinking that you're over the Atlantic and you're depending on the combustion stability of rotating detonating waves to go home, that's even a less pleasant thought. So I think there's still a way to go for that to be applied.
Yeah. Purdue is doing quite a bit of research, and I remember a few years ago they managed to get a few waves going, but they couldn't really predict how many waves they would get going, which tells you the issue.
I think there's some research that has advanced into that. In a sense, they are relatively stable, but still not stable enough for operational use.
Yeah. Okay. Let's see if anybody else has any more questions for Dr. Marcu.
Well, I mean, I guess at this point it's clear we can also take questions from guests. So I'm sure Albert had at least one.
Oh,
there it is. Prepared and ready to go.
Okay, so Albert is asking a question about hybrid propulsion systems. Are those alternatives still used today? I guess we could benefit from both the high thrust of the solid boosters, but also from the flexibility of the liquid propulsion systems, turning on and off the engines.
There have been attempts. I'm not very familiar with them because I didn't work on any of the systems, and I wasn't curious enough to read a lot about them. From my knowledge of the industry today, I don't see them used in any wide range, and everybody's following in the footsteps of liquid chemical propulsion. I'm sorry for Albert, there was a short question, but I'm not aware of any other details.
Okay, thank you for your answer. Before other people write questions in the chat, I was curious about your thought on maybe the current design challenge in terms of rocket propulsion. What do you see? What could be the next step, or what's the biggest challenge that you think the design industry is facing at the moment?
I think one of the challenges is that there are too many people reinventing the wheel. All these new companies are essentially redeveloping the same engine, an engine of about 150,000 pounds of thrust. They tailor it to their specific needs. But that's my very personal opinion, by the way. It's not official. It's too redundant and it's not efficient. So I was back at Rocketdyne in early 2000s. Rocketdyne was a relatively rigid corporation, and it was hard to push new ideas. But I made a presentation and talked to a few people about a Formula One engine that was called the Cosworth engine back in the 70s through 80s. The Ford Corporation has generated a design of a F1 Formula One engine that was then, say, available to everyone that wanted to generate, to design the vehicle. So for a number of years, maybe a decade or so, there are many teams other than Ferrari and other specialized integrated companies that were not per se car companies, but they were just Formula One teams, and they would use the Cosworth engine for their vehicle. So in parallel, I thought of proposing to Rocketdyne to generate a Cosworth rocket engine, which would then be made available to the industry of all these startups. And at that time, SpaceX was just starting. And there were some signs like early spring where you see the little buds of green that's coming, that this is coming, and I thought it's a good idea. It didn't catch, and people evaluated the risks, and there is a risk that all these companies will have accidents and so forth, and together with liabilities. So in the conditions where everybody is now designing rocket engines, and none of them are doing it on a large scale production, except maybe SpaceX, they are not making the product low cost, because essentially that's the big problem with rocketry. They're all expensive. Market will decide which of them stay in business or not. So that's not an engineering challenge, but more like an economic challenge, if you want. From the technical point of view, the only way to go to more performant engines is to increase the pressures and temperature for that matter. But this again, you reach the level of material limit. You will improve materials, will invent new materials, will tailor the cooling and so forth even better. But it's pretty much like the internal combustion engine for the cars. We need a new paradigm, pretty much like the Teslas have become the new paradigm of automotive cars. If you're driving a Tesla and compare it with your older car, you realize the difference. It's a completely new paradigm. The acceleration, the ability, the efficiency of it's much better. So, and then you have a critical technology, which is the battery technology. I'm not sure if that's available. That is the subject of my book. What if someone is thinking of a new way of producing rocket thrust?
Okay.
Yeah, so I haven't seen that yet, except in a literal way. Yeah.
Well, thank you. That's quite an interesting point of view. And do you think this paradigm shift is very much needed at the moment, or we haven't really reached, let's say, the point where the rocket propulsion technology is really the choking point of the industry? Have we reached that or not yet?
No, I don't think it's a choking point. I don't see it as that. I think that we're going through a soul-searching moment, if I call it that way. I am worried about having 12,000 satellites by just one company in space. Okay, and it's not just them, because then OneWeb is following. Us at Blue Origin are coming with another 3,000-4,000. So not going to the Kessler effect, where if these things collide with each other, then it's a matter of time when we're just surrounding by a lot of junk in the low Earth orbit. But assuming that's not happening, it's still something that amounts similar to the pollution on the Earth. Fortunately, these LEO satellites are able to lose orbit and burn into Earth after 5-6 years. So, but depending on how these business models will pan out, somewhat a reorganization will have to happen, so where we're going back to the model of specialized providers. Because 20 years back, there will be a company that produces engines, there will be a company that produces rockets, and then there will be an integrator of some sort. SpaceX has introduced the integrated model where you do everything: engine, rocket, avionics, integration, and operations. Right now, that's the golden standard. Everybody wants to do the same, but reinventing the wheel. So time will tell. But I don't see any specific choking point other than money.
Okay. Thank you very much.
Yes, and thank you to Anka about the Kerbal Space explanation. I'll take a look. I've never played that game prior. So it looks like Age of Empires in a space environment. Yeah. Yeah, I guess we're also reaching the time of on my end, because I need to leave the hotel and start moving. But I'd like to thank everyone participating and listening to this. It's been excited on my end as well.
Yeah, we're extremely grateful to have you here with us. You're literally living proof of what can be accomplished. And I think that's very inspiring for the Romanian youth that we have here. And,
yeah, we had an interview done for NASA a while ago. We got a bit carried away because we were having a little bit of whiskey while having this 2 hours interview, but the message stands. Back in the day, when during communist time in Romania, when I was an engineer, we had a big missed opportunity, because we had the mentality then of not doing things. We were thinking, oh, it's not us. I mean, there are all these others, like the British or the Germans or the Americans, they are doing the true things. We didn't realize at the time that we had the means, but not the liberty, because of the narrow minds in power at the time, that all we had to do was start making machines, start making turbines, start making engines, break them, burn them, do mistakes, but keep trying. We had the material base at the time. What I'm hoping now in Romania, there is a new generation of small companies that are increasing in terms of business models and so forth, not necessarily rockets and aerospace, but we have to get this mentality of, yes, we can do it. All you have to do is start doing it. Please trust me, this is the secret. Yeah, my parting message. Thank you, everyone. We'll see you soon.
For your presence, and hopefully we'll have you back in our lectures soon.
Sure, we'll do that. Thanks, Adrian, Maria, everyone else.
Thank you so much. Have a lovely day ahead, and we'll see you.
Thank you.
Bye-bye.